Okay, it's 5:25, so let's get started. We're getting there. We're almost there. We got to grade the final exam in 2 days. So I have to grade the final exam from Wednesday to Friday of next week. I'm going to do it by myself. So write succinctly. All right. Announcements. Set 5 is still out, and it's due when? Tuesday. Any questions about set 5? Guess everyone's doing set 5 well then. Okay, no questions on set 5 then. Final exams on Wednesday, so any questions about that? You covered that last time. Other questions?
Yeah, exactly.
Well, so I'll tell you what'll happen. You'll get a bunch of pieces of paper with some black ink written on them, and your task is to transfer some other either graphite or ink onto the page and hand it back to me in an optimal way. All right. Other questions about the final? No questions?
And there's going to be a review on Friday.
Yep, and one today.
And office hours.
Yeah. So I'll tell you what's going to happen today and Monday. But any other questions about the final? Okay. So what's going to happen today and Monday? What I'm going to do is I'm going to lecture for an hour on basically computational complexity at large. So we saw a little bit of it, and then I'm just going to give you a whole grab bag full of neat and interesting stuff. It's not on the final whatsoever. So this is just a way for you to relax and see what other things people are actually working on, what people are interested in, that sort of thing. Then the last half of class, we'll do an extra final exam review. And so in office hours, it's just normal office hours. On Monday, I'll talk for an hour about my research, then final exam review with office hours as well. Okay, I think that would be enough final exam review. Any questions about that? Okay, so what have we talked about in terms of, well, really the entire class? Well, we talked about problems that we can recognize or decide with certain models of computation. So DFAs, NFAs to start off, and then we talked about CFGs and PDAs, then we finally went all the way to Turing machines, saw some things were not decidable, and then we decided to say, okay, there's no point in talking about things that are not decidable because I can't write a computer program to do that. So what would be more interesting is the things I really can recognize or decide within a small amount of time. And we defined that to be P for polynomial time. And then we thought of an analog of that, a generalization for non-deterministic machines, which is NP. And we were able to show that P was a subset of NP because based on the definition and the fact that NP can also be defined in terms of a polynomial time verifier. Well, a verifier could just run a P algorithm anyway. So P is a subset of NP. And we saw some problems that we thought were NP complete. So this is kind of like a diagram saying we're going, problems that are more hard are to the right and problems that are easier are to the left. So right at the very edge of NP of NP, we saw NP complete problems like 3-sat and clique, independent set, and a whole bunch of others. But then we thought, well, we can talk instead of talking about time, we can talk about space. And then we defined this notion of P space. And we saw that NP was a subset of P space because we can simulate one of the NP complete problems with a small amount of space by just reusing the space. So we saw that NP was a subset of P space. And you may be wondering, okay, we did this for NP. What about a non-deterministic version of P space? Well, we showed by Savage's theorem last time that this is equal to NP space. And Savage's theorem is more general, which will actually have implications when we talk about low space complexity in a bit. But we saw that P space was equal to NP space. And we may think, well, are there any problems right here that are P space or NP space complete? So we say that that L is P space. So I'm not going to prove a whole bunch of things today. I'm just going to tell you about some of the cool stuff. So is P space complete if L is in P space and for, I'll say, and every B in P space Pauli reduces to L. So it's exactly the same notion of completeness for NP, but now we just require the problem to be in P space. Okay, so what is a problem that's in here that is P space complete? So one of the problems that we saw was NP complete was 3-sat or satisfiability in general. Well, or CNF-sat in general. Well, what we could do is make a generalization of that. So instead of saying there exists an assignment to satisfy the formula, maybe we can say, okay, for this particular variable, there exists a value either true or false to make the formula true, but this variable, both assignments to true or false have to make the formula true. So if either one causes the formula to be false, then the formula is unsatisfiable. And so we can see that CNF-sat, or sat in general, is just saying there exists a value for this variable, there exists one for this one, exists. But now it's a generalization where we can say this variable, you have to have both of them be true. So this problem is called TQBF. And this is an acronym for totally quantified Boolean formula. And the structure of the formulas look like Q1, X1, Q2, X2. Let's say there are M of them. And then an arbitrary formula. You can think of it as CNF if you like. Well, each of the QIs is either an exists or for all.
Are those adjacent or is there an operator?
It doesn't matter. So I'm skipping a bunch of terminology here, but the idea is that there's kind of a scoping thing going on. So like anything to the left of QM, that's outside. So this is what is called pre-next normal form, but we won't get into that. The idea is that if we had, let's say, exists x1 for all x2 such that x1 or x2 bar and x2 or x1, that says that there exists an x1 such that for every value of x2, the formula is true. So does there exist a value of x1 such that both assignments to x2 make the formula true? Well, let's see. I actually just made this up on the spot, so I don't even know. So let's look at the two cases. Well, if x1 is true, does no matter what assignment I make to x2 still make the formula true? Well, let's see. If x1 is true, I think I just satisfied both of those clauses. So no matter what, the formula is true in that case. So therefore, since this guy is a clear winner, this formula is satisfiable. And I'm here to say that TQBF is p-space complete. It's in p-space because we can simulate one variable and then just keep a record as to which of the variables that we've seen so far, and then do a recursive call. And then we note that there are only polynomially many recursive calls. As to show that TQBF is p-space hard, well, we follow the same proof as we did with Cook-Levin, but the idea there falls apart because whereas with Cook-Levin, we guarantee how long the formula or the computation really is. Here, it could be exponentially long because we're only bounded by how much space we use. So the idea here is to exploit the exists and for all such that if you have C1 and C2 and there exists a C such that C1 can yield C prime and C prime yields C2, then you have a for all variable that says both of these are true. And that cuts down on the formula size enough to make it polynomially sized. And so therefore it's p-space hard.
And that specifically is the for each, the p.
Yeah, exists, yeah. So the proofs in the book, I'm not going to go over the proof, but that's the basic idea. And if I show that it's in NP space, by Savage's theorem, it's in P space too, because those classes are the same. Okay? Any questions about those two, about TQBF and P space complete?
So to say that it's p space complete, we have to prove it's in in p space and it's p space hard?
Yes, P space hard meaning that every problem reduces to it, or a P space complete problem poly reduces to it. Exactly the same as NP, but now we're in P space. Yep, and so here we can put TQBF as a P space complete problem. Okay, so I'm gonna copy this down because I'm gonna be using it again. So we're starting to get a little higher on the hierarchy here, but you may think, well, certainly this can't be everything that we study, right? What about problems over here, or that are harder supposedly than p-space, or problems that are supposedly easier than polynomial time? So we're going to look at both of them. So we're going to look at the lower side first. Well, in order to talk about the lower side, we need to have a notion as to, well, what is less than polynomial time? Well, that includes the whole input. But I can't read the whole input in less than linear time. But what about, say, less than linear space? But that also doesn't make sense because I need to store the input somewhere. But maybe we can have a model of computation where we do not modify the input at all, but we only use a small amount of extra space. Okay? So the idea in this setting is that we have input right here that's completely unmodified. It'll never be touched again. You can look at the input, but you can't write onto the input. And you have something that's called a work tape, where you do the work, and then something called an output tape, which you may or may not use, but it's there if you need it. And so why would you want a small amount of space or study a small amount of space? Well, the idea here is that if you have a really large input that you can't store, maybe it's streaming by you, maybe you want to only work with a small amount of it at a time instead of storing the actual whole thing. For example, if you're streaming a bunch of Twitter tweets, which you obviously can't store everything, but if you analyze them as they're coming by, maybe we can talk about a model of computation for that. So let's see where my notes are. Yeah. So we're going to define L to be space of log n, and NL to be n space of log n. And I can't use Savage's theorem to show that L equals NL, because Savage's theorem only guarantees that you get a square on the argument in terms of n space and space. So we know that by Savage, n space log n is a subset of space log squared n. Because Savage's theorem, you get a square on the bound. So space log n and space log squared n are not the same. Well, they may or may not be the same. It's not evident that they're the same here. They actually are different. But Savage doesn't say anything about L and NL. And actually, an open question that still exists today is, does L equal NL or not? Most people believe, no, they do not, or they're not equal. Well, like we did with NP and N space, which is P space, do we have a completeness type problem for NL, let's say? So we can't work with polynomial time reductions here because polynomial time is at least as long as log n space. Why is that true? One argument that you can say is that you can show that L is a subset of NL, obviously, but that's a subset of P, polynomial time. And the argument is that, well, if you only have constant times log n space, well, the number of possible configurations is some constant to the constant times log n. But that ends up being some polynomial. So we can simulate all possible configurations in polynomial time. So therefore, NL is a subset of P. So if we wanted to find NL completeness in some way, then we can't work with polynomial time reductions. So we'll work with what are called logarithmic space reductions, because we can't have the reduction be more powerful than the model we're talking about. So we say that, I should not use L here. We should say that A is NL complete if obviously A is in NL, and for all B in NL, B logarithmically reduces to A, which means that the reduction from B to A only uses logarithmic space. Instead of using polynomial time, we use a small amount of space to change the problem from B to A. Okay? So what's a problem that is in L or NL? In fact, A DFA is in L. We showed that it was decidable before, but it actually exists in a really low class here called L. Why is that? Well, what things do you really need in order to figure out whether a DFA accepts or not? Well, what you need to keep track are the state that you're currently in and the character that you're going to read. Well, how would you use that in logarithmic space? You just keep a pointer to the original input and then just read off the input. So you only have two pointers, essentially, which is a constant, so therefore you're only using constant times logarithmic space. So ADFA is in L. Well, another problem that's along that lines but is a little generalized is called path. So you're given a directed graph and two vertices. So it's a digraph. And there is a directed path from S to T. Okay, well, we actually do not know whether this problem is in L or not. And if we figure what the answer is, yes or no, then we can settle whether L is equal to NL. Well, how could you show that path is actually in NL, in non-deterministic log space? Well, what you do is you start at S, and you make a non-deterministic transition to one of the vertices that is adjacent to S. And then all you keep track of is the current state that you're at. And that's only constant times logarithmic space. And then if you ever reach T via non-deterministic transitions, then there is a path. But by non-determinism, if you never reach T, then S is not connected to T. So I don't even need to keep this frontier like in breadth first search or anything. I can just do non-deterministic transitions. Okay? Well, we talked a little bit about this class called co-NP, which is the set of all problems whose complements are in NP. Well, in here, we can actually show that path is in co-NL, the complement of NL. Well, how would you show that there is no path from S to T using only logarithmic space non-deterministically? That seems quite difficult and quite a different question than just guessing whether there exists a path by just guessing vertices. And the idea here, so there's an entire algorithm in the book. I highly recommend you read it. But the idea here is that you determine how many vertices that you could reach via one transition, and then you figure out how many you can reach in two transitions, and now you know how many vertices are on this second frontier, two edges away. Then you look and keep going, yeah.
Since you mentioned the book, could we get an update on the schedule for which parts of the book are being covered in the last?
I mentioned that last time. So none of this. Only up to NP completeness.
But for those who are trying to read the book.
Through chapter 7. Yeah, and not chapter 6. Okay. So how would you? So we showed that path is in NL and path is in co-NL. How would you show that path is NL hard? Well, what you do here is that if you have a logarithmic space algorithm, could you make a directed graph based on the original, the computation that took logarithmic space? Well, the idea here is that you make what is called a configuration graph, and you make a vertex for every single one of the configurations. So there's more to this than this, but the idea is you make a vertex for every possible configuration in logarithmic space, and then make an edge if there's a non-deterministic transition from one to the other. And then you ask the question, from the starting configuration, could you get to any one of the accepting ones? Yeah.
We talked about before that you could do the complement of a graph to find, the, like when we talked about the complete. Is that another way of doing it too? Because then you could, if there was, if you could the complement of the digraph, then would you?
So I think that is a logarithmic space reduction from clique to independent set. But I think the problem there is, you have to be careful about how much space you use.
Okay.
Yeah. The model varies very much differently depending on whether you could say how much you can write to the output tape or what you could do on the work tape. It really depends on what the model is.
Yes, and I guess if it's a diagram, it's not the complement may not also be a diagram, right?
Yeah, it would still be a digraph. Yeah, you would just, for all n, choose 2 different possible edges. Yeah, no, it's not n choose 2, it's n times n minus 1, because you can have it going in both directions. Then you just make an edge that wasn't there, make it be present, and flip, yeah, so it would still be a digraph. But I think the analysis wouldn't work that well. There's something you need to check about that. Okay, so we can show that path is NL hard, and as a result of that, we have that NL equals co-NL, which is pretty surprising. As we saw, for non-deterministic, for polynomial space, they are the same, but it's a completely different question for logarithmic space, but they in fact are the same as well, which is pretty surprising. Okay, so let's take a brand new look at the world that we currently live in right now. Well, L is a subset of NL, but that equals co-NL, which is a subset of P because we can just simulate every possible configuration in polynomial time, which is a subset of NP. And we don't know the answer as to whether that is equal to co-NP or not. That's a subset of P space, and that's equal to NP space. And that's what we've seen in the complexity world so far. And I'm not kidding when I say this, there are thousands of complexity classes people study. So this is just a small window into some of them. So I'm gonna talk about quite a few more. Okay, so, well, what about up here, right? If we want to talk about maybe something that's harder than P space complete, maybe we can say something about how that relates to some of the smaller classes. And so we can define a class called exp time, and that's the union over k at least 0 of time 2 to the n to the k. In other words, you run for an exponential amount of time, or up to exponential time. Well, I claim that P space is a subset of exp time. Well, why is that? The idea is the same as showing that NL is a subset of P. How many possible configurations are there? Well, if the length of each configuration is polynomial in size, well, 2 to the polynomial, well, that is what exp time is defined to be. So therefore, P space is a subset of exp time. Okay? Any questions about that? Okay, so over here, so I'm not going to talk about X time complete problems. So this is the world we live in, and we can talk about, say, double exponential time, triple exponential time. We can keep going as long as we want. Okay? Well, let's take a look at these containments again. So I'm going to copy it down. Oops. Saved it. All right. So I'm going to delete these because I don't need them. Well, of course, as I mentioned, one of the big open questions is whether P is equal to NP, something that no one knows. So we don't know anything about that containment, whether it's strict or not. We also don't know anything about whether NP is a subset of P, whether NP is equal to P space or not. In fact, all 5 of these, we have no idea whether they're true or not. But we can say something else. I claim that NL and P space are different. And so one of those 3 containments in the middle must be strict, but we don't know which one. I can also show that P and X time are different. So therefore one of those 3 is also strict, but we don't know which one. And so why are those true? The first one is due to something called the space hierarchy theorem, which says that space of O of f of n is not equal to space of little o of f of n. And the idea there is to show that if you have any problem that runs in O of f of n space, use a diagonalization type strategy as we saw for ATM to make it always different than any machine that runs in little o f of n space. And therefore we get that result. And so therefore, since we have non-deterministic log space versus polynomial space, therefore they must be different. In fact, any space in between, say n to the 1.1 versus space of n to the 1.2, those are different. And in any function, so there's another thing that you need to say here, but basically this is any amount of asymptotic increase in the function, you get more languages, which is pretty surprising. And for the other one, there's something called the time hierarchy theorem, which says that, so this one you need to be a little more careful. So time of O of f of n is not equal to time of little o f of n divided by log n. And both of these are in chapter 8 and chapter 9, respectively, in the book, if you want to take a look at these. The idea there is exactly the same, but the problem is in order to compute how much time you're going to actually use, that takes time to actually write out it. Whereas for space, you can just write out the however long f of n is in O of f of n space, and therefore you're good. But time, it takes up time to write that number out, and therefore you get a log factor reduced. But because of that, if you talk about polynomial time versus exponential time, those are different. And in fact, if you want to talk about things running an O of n time versus O of n squared time, those are different too. Because if you increase it by n, that's more than a log factor. Okay? Cool. So, any questions so far? So, I have my independent study here, and I'm trying to think what would be interesting. Okay. But any questions so far? Okay, so we're going to take a little bit of a detour from machines and talk about something that's called a circuit, which is a different model of computation than a machine. Well, you can think of a circuit as it takes a bunch of inputs and it produces some output via how the wires interact with each other. Okay? So a Boolean circuit is a directed acyclic graph with source vertices, as we're going to call them. So you can think of those as your input pins, let's say. A sink vertex. So the first set are your input pins, maybe, and you have exactly one output. And the inputs can be set to 0 or 1 each, and therefore the output vertex will be a 0 or 1. So, and we also have a bunch of what are called gates. And these are vertices with what is called fan-in 2. So fan-in means the number of edges coming into that vertex, and you can guess fan-out means the number of edges leaving. So you can think of gates as you're receiving 2 inputs and is going to produce exactly 1 output. So think of, like, say, an AND gate. It takes 2 inputs and produces the AND of those 2 bits. Okay, so fan-in 2 and fan-out 1. So for example, if we have, so here are my wires here, and let's say that I connect them up to an AND gate right here. I think we have a NOT, yeah. So we also have another one called NOT, which is fan-in 1 and fan-out 1, because it only takes 1 bit and complements it. So let's say that I feed the third one into a NOT gate, and then I OR these, let's say, and then I AND the last 2. So these are my source vertices, and that's my sink. And of course, if you want to think about, I want to have an arbitrary number of inputs to a given gate. So like if I had like 10 different wires coming into an OR vertex, you can actually simulate it with fan-in 2 gates. The idea is that you feed the first 2, and then take the output of that, feed the third one and that output together, and then you feed the output of that and the fourth one together, and then all the way through. And all of those are fan-in 2, fan-out 1. Okay, so we can do that. And then we say a T of n size circuit family. So this is a different model of a computation that models kind of what a Turing machine would do on all possible inputs. So is an infinite set of circuits. Let's call them C0, C1, C2 for all integers. And where all of the CI have size at most T of n. Yeah, so I should say the circuit family for a language L, and for all inputs, yeah, I should say, for all inputs of size n, Cn outputs the correct answer. Because if I want to look at our circuit before, we have 4 input pins. There's no reason for this circuit to take an input of length 5. So that's why a circuit family needs to be an infinite sequence of circuits, because it needs to work with all possible input sizes. So And we say that it's a circuit family for a language L if all inputs on the associated circuit that takes that many inputs outputs the correct answer. Okay, so I don't know what the language of this one is, but actually it wouldn't have a language. So I don't know what inputs this particular circuit will say 1 onto, but if I have an infinite sequence of them, then I can talk about it accepts these ones of length 0, these ones of length 1, these of length 2, these of length 3, and all the way through, yeah.
And the accepting this one is meaning true from the outside?
Yeah, if it outputs 1, it's true, yeah. Yeah, so the major question is, for NP complete problems, does there exist a polynomial size circuit family? Because if there is, then I can just look up the associated circuit, run the polynomial size circuit because it's a directed acyclic graph, and therefore I can answer the question in polynomial time by just feeding it through the circuit. So instead of thinking of it as a machine model, you can think of it as feeding bits through a circuit and then figuring out what the output bit is. So let's see. Let's consider this language. The language of only ones. Well, this can actually be decided by a linear size circuit family because I just take an AND gate for the first 2 bits, feed the output of that to the 3rd bit, and AND those together, and then do the same thing through the rest of the input. And that's linear size. Okay. So what we're going to define next is an analog of having polynomial size. So the language P poly is how it's pronounced, is the union over all C is at least 0 of languages accepted by poly-size circuits. So L1 would be in P poly, that sort of thing. And I'm not going to prove it here, but P, it turns out to be a subset of P poly.
Is that P minus poly?
No, it's a different arrow. Yeah, they put a slash here for a good reason, because you can also talk about, say, having logarithmic size circuits or with polynomial time, and you can extend this to different size circuits and all that stuff, or different, yeah. So it's just a name. It doesn't really have anything to do with P itself, but there is an analog of it that does. Okay, and this is actually strict. And why is that? Well, consider.
What does strict mean?
Yeah, so strict means that there is some language in P poly that's not in P. In fact, P poly is a what is called non-uniform language. So where we had P is a subset of NP, which is a subset of P space, which is a subset of X time. It's a uniform hierarchy. This just intersects in a really weird way. And why is that? Let L be any unary undecidable language. Then L is in P poly. And the reason is for any of the inputs for any of the strings in the language that don't have a certain length, have that circuit be empty, and any one that is that does have a string of a certain length, make it and of all ones, because it's unary here. And what would an example of a language be? Let's think of a good example. It would be 1 to the power the length of a machine, mi, let's say, and mi, no, that's not quite right, mi and w MI is the ith Turing machine that accepts W. Well, it seems pretty intuitive that this is undecidable. Because if I can determine this, then I can pretty much determine ATM. But that's undecidable. So this is a very strange class. But, well, 355 is too. But this is actually a very strange class. But you can actually redefine p-poly in a different way. So you can think of p-poly instead of circuits. You can think of running in polynomial time with access to what are called advice strings. So kind of like non-determinism here, but you have this sequence of infinitely many strings available to you, and you can access a polynomially many of them. And that actually turns out to be an equivalent definition. So defined as the set of all languages that can be decided in polytime with access to an infinite sequence of advice strings. And the great thing about this is that you can say what the advice strings look like. So, for example, it's the set of all satisfying assignments for inputs of a certain size, for example. And the way that you prove that p-poly in this definition is the same as poly-size circuits, essentially all you do is say the ith advice string, that's the circuit of inputs of size I. And so you make the circuit be the advice string and vice versa. Okay? So I have like 10 minutes to see what I can do. Ooh, that would be difficult. Is there? No, I want to show you some really cool stuff. Okay, yeah, so this is pretty cool. So, and computational complexity, I will conjecture, is the largest theory field in computer science. So I'm glossing over tons of details. Thousands of people are working on many, many different problems here that I'm just glossing over. Well, what about figuring out, let's say, for an NP-complete problem that we don't know whether it runs in polynomial time or not. But maybe we could figure out what of the problem is the hard part, and then extract it out, and then say, okay, the rest of it is easy, but this certain part is hard, right? That might be really useful. So that is an area called, and it's very hot right now, called parameterized complexity. Okay, so the idea here is that you're given what is called parameter of the problem, and we'll see an example of it. You're given a parameter of the problem or language and the language itself, and then you want to say, in terms of the parameter, how long does it take to solve this problem? Okay, so we're given a language L and what is called a parameter K. Okay, and what you want to say is that you're given a string that may or may not be in the language, and you want to determine whether it's in the language in some amount of time, maybe depending on K. Okay? So we'll define two languages, not languages, computational complexity classes. The first is called XP. I know what the meaning of it is, but I always love the the acronym experience points. But it actually is called slice-wise polynomial for many reasons. But this is the set of all pairs L and K, such that given W, determine if W and L in the length of W to some function based on the parameter K. And this function F can be arbitrary as long as it's computable. If you can actually compute the value of f of k in any amount of time, then if your language can run in the input size to that value in that amount of time, then therefore we say it's an XP. And the problem here is that you're making the function that's based on the parameter be arbitrarily large, and the input size to that extremely large number in general, that's not something that could be run efficiently. So there is another language called FPT, and it stands for Fixed Parameter Tractable. So the idea here is that if you have the parameter size be fixed in size, then you run in polynomial time. Okay, and so the language here is LK, such that same thing, but we can determine it in polynomial time in terms of W times f of k. So instead of having this huge value that's dependent maybe on the input in the exponent of the length of the input, then it's just only a multiplicative factor times only a polynomial in W. So we get efficient runtime in W, but maybe a lot in terms of K. But if K is really, really small, like 2 or 3, then that is still polynomial in size. So we really are extracting what is the hard part of the problem here. Any questions? Okay, well, it's pretty obvious that P is a subset of FPT because we can just ignore the parameter and just run in polynomial time. And that's a subset of XP as well. But we don't know whether these are strict or not. Okay, so so I'll do one problem and then we'll stop. So we talked about this problem vertex cover, and we showed that it was NP complete. Well, how would we put it into the setting here? Well, we talked about given a graph G and an integer K, determine if there's a K size vertex cover in however amount of time. Well, maybe what we have here is what is called the natural parameter, which is K, because we're given G and K. So K here is what is called the natural parameter. So we'll define what is called K vertex cover to be the set of all graphs in K. So G is a graph with a K vertex cover. So we'll actually show that it's both in XP and in FPT. So how do we show that KVC is in XP? And I'll just remind you of the runtime. So how do we do that? Well, think of this. Just run through all possible K choices of vertices, all possible sets. And for each one, determine if it's a vertex cover. So let's see. Look at every single K choices of vertices. Determine if vertex cover for each. Well, what is the runtime of that? Well, an easy upper bound is saying, well, that's just the number of vertices to the k, because I'm just picking k things out of the number of vertices. So we can see that the algorithm runs in O of v to the k, and I have to put a +1 here because I need to check for each one that is vertex cover. But let's see. Is that an XP algorithm? Well, is it of the form the input size to some computable thing? Well, the input size is roughly the number of vertices. To the power is k plus 1 computable from k. I hope so. Can I add 1 to k? Yeah. So therefore it's an XP. Okay? But it's pretty evident there that we're just doing a brute force algorithm and we're not really extracting the parameter out like we are in FPT. So how do we show that we can actually go down to FPT for this? Well, let's see. If I have, let's just say that I pick an edge. If I look at some edge, do I need both vertices in the vertex cover to cover that edge? No, I only need one of them. So maybe what we can do is pick, for any edge, pick one of the vertices, and once you pick that vertex, delete it. And try again, k minus 1 more times.
Wait a second. Delete
the chosen vertex and all adjacent edges to it. Because if you pick that vertex, there's no point in picking all the other edges. And so then we'll have that repeat k minus 1 more times. So that I'll have k vertices. At the end, if I have any edges left, that particular choice wasn't a vertex cover. So try again if it's not, and repeat. Well, how many possible choices of vertices are there? Well, I have 2 choices every single time. So 2 choices times 2 choices times 2 choices times all the way down, I have k choices to make. So this ends up being a 2 to the k time algorithm. So the idea here is pick a vertex, pick an edge, and an arbitrary vertex, then delete it, and all adjacent edges to it. Then by our analysis, this runs in 2 to the k time, because I'm just doing k choices each time. Well, let's see. For each one of those, how do I determine if it's vertex cover? Well, it's just the size of the graph once I delete those k vertices to check if there are any edges. So that's the size of the graph times 2 to the k. So this, So this, it doesn't run in 2 to the k time. There are 2 to the k repetitions. And so therefore we get a runtime of O of, say, the number of vertices times 2 to the k. And is that of the form input size times some function only depending on k? Is 2 to the k only dependent on k? Say yes. Yes. So we can now see that it's in FPT. So by that algorithm actually does extract out what is the hard part of the problem. Okay, and there's a huge literature on this subject called parameterized complexity, like what are called parameterized reductions, where you transform from one problem to another. there's a whole, what is called a hierarchy of problems that we still don't know if there are any strict containments in between. But there are many other types of things you can look at. Say, if the Turing machine fails on some constant fraction of the inputs, what else could you recognize? If you want to talk about cryptography, for instance, if you want to talk about having parties compute some function by talking to each other, what functions could you talk about there? There are many other things in terms of that. So I think that's enough. Any questions, though? I think we're due for a break, so let's take a break.